If I told you that the little magnet stuck on your fridge right now only works because of Einstein's theory of relativity, you'd probably think I was messing with you. Magnets feel like the simplest thing in the universe. Two ends, north and south, opposites attract, same poles push apart. End of story. Right? Wrong. Dead wrong. And by the end of this video, you're going to look at every magnet you own completely differently. Because almost everything you were taught about them in school was a simplified lie designed to make your third-grade brain stop asking questions. Here's the real story, and it gets weird fast. Stick with me, because the twist at the end of this video is one of those facts that once you know it, you cannot unknow it. Let's start with the question nobody ever asks. What actually is a magnet? Not what it does, what it is. You were told there's this invisible force field around certain metals. Fine, but where does that field come from? Why does a chunk of iron have it and a chunk of aluminum doesn't? Why does heating a magnet up destroy its power? Why can you never, ever find a piece of a magnet that has only a north pole and nothing else? Break a magnet in half, you don't get a lonely north and a lonely south. You get two brand new, complete magnets, each with their own north and south. Snap it again, same thing happens. Keep going down to a single atom, and it still happens. This single fact has haunted physicists for over a century, because it means something is fundamentally different about magnetism than almost every other force we know. Physicists call it the magnetic monopole problem, and here's the wild part. We have never once in the entire history of experimental physics detected a single isolated magnetic pole on its own. Not one, ever. Meanwhile, electric charge, the thing magnetism is supposedly related to, comes in single isolated units all the time. A single electron, a single proton. So, if magnetism and electricity are cousins like your textbook claims, why does one of them come in solo units and the other refuses to? This is the open loop. Keep it in your head because we're coming back to it and the answer is going to break your brain a little. Let's talk about where magnetism actually comes from, because this is where things get good. Every single magnet you have ever touched, from the one on your fridge to the massive ones inside an MRI machine, is made of moving electric charge. That's it. That's the entire secret. Electricity in motion creates magnetism. Always. No exceptions. Run electric current through a plain copper wire and wrap it in a coil, and suddenly that wire becomes a magnet, strong enough to lift a car if you scale it up, which is literally how junkyard electromagnets work. Turn the current off, the magnetism vanishes instantly. So a magnet is never really a separate thing. It's a side effect. It's what electricity looks like when it's moving. Now here's where your fridge magnet gets interesting, because there's no visible wire, no battery, no current flowing through it that you can see. So where's the moving electricity coming from? Inside every single atom in that piece of metal, electrons are spinning and orbiting the nucleus. And each one of those electrons is a microscopic loop of moving charge, which means each electron is its own tiny magnet. In most materials, these billions and billions of tiny electron magnets point in random directions, cancelling each other out completely, which is why a piece of aluminum or wood or plastic shows zero magnetism even though it's absolutely packed with spinning electrons. But in a handful of materials, iron, nickel, cobalt, and a few rare metals, something strange happens. Neighboring atoms actually force each other's electron spins to line up in the same direction in patches called magnetic domains. When enough of those domains point the same way, all those tiny individual atomic magnets add together into one giant magnetic field you can actually feel. That's your fridge magnet. It's not one magnet. It's trillions of microscopic magnets standing at attention in formation, and this explains the mystery from before. You can never isolate a single pole because you can never isolate a single spinning electron loop and keep only half of it. Break the metal in half. You just get two smaller formations, each one still a complete tiny army with both a north and south end. The loop can't be cut in half, so the poles can't be separated. Mystery solved. But we've only scratched the surface, because now we get to the part that made even physicists uncomfortable for decades. Quick pause here, because I want you to actually picture this. Imagine you're floating right next to a single moving electron, matching its speed exactly, like you're sitting in a car right beside it on the highway. From your point of view, that electron isn't moving at all relative to you. It's just sitting there. And here's the insane part. If the electron isn't moving relative to you, there is no magnetic field. None. Magnetism literally disappears. But if you step outside that frame and watch the electron zoom past you, now it is moving, and suddenly a magnetic field appears out of nowhere. Same electron, Same moment in time. One observer sees pure electricity with zero magnetism. Another observer, moving at a different speed, sees electricity and magnetism. That should be impossible. Physics isn't supposed to change depending on how fast you're walking. But it's real. It's been tested, and it's called relativistic electromagnetism. Magnetism isn't a separate force of nature bolted onto electricity. It's literally what electric fields look like once you factor in Einstein's special relativity, which shows that space and time themselves shift depending on how fast something is moving. Magnetism is the universe's way of keeping the laws of electricity consistent, no matter your speed. That compass in your pocket, silently pointing north right now, is running on the exact same equations that describe black holes bending time. Let that sink in for a second, because we're not done. There's a twist coming that even bends this idea further. You'd think, okay, so a magnet is just a line spinning electrons. Cool, mystery closed. Except there's a second magnetic effect happening that has nothing to do with electrons spinning around the nucleus like tiny planets. Electrons have a built-in property called spin, and despite the name, it isn't actually the electron physically rotating like a top. Nobody fully agrees on what it truly is at the deepest level, but it behaves exactly like a magnet on its own, independent of any orbiting motion, purely from quantum mechanics. This is one of those places where physics stops giving you a clean visual metaphor and just says the math works. Deal with it. Most of the magnetism inside iron, nickel, and cobalt actually comes from this quantum spin property lining up across atoms, not from orbital motion at all. So the fridge magnet in your kitchen right now is being held up on your fridge door, partly by a property of the universe that we can accurately calculate and predict with stunning precision, but cannot fully visualize or explain in plain human terms. We can use it. We can't picture it. And here's your mid-video twist. The thing almost nobody knows. If you heat a magnet up hot enough, it loses its magnetism completely, permanently. And the exact temperature where this happens is called the Curie point, named after Pierre Curie. Heat gives the atoms enough energy to start jiggling around chaotically, which knocks all those neatly aligned electron spins out of formation, back into random directions that cancel out. For iron, this happens at over 750 degrees Celsius. Cool it back down, and depending on the material, the magnetism can return as the atoms settle back into alignment. This is exactly why Earth's magnetic field, the one keeping your compass pointing north and shielding you right now from deadly solar radiation, doesn't come from a giant permanent magnet sitting inside the planet's core. It can't. The core is way too hot, thousands of degrees, way past any Curie point. Instead, Earth's magnetic field comes from something even wilder, swirling liquid iron in the outer core acting like a massive natural electromagnet constantly generating current through motion, the same electron loop trick from earlier, just on a planetary scale, millions of times over. And that field, generated by molten metal thousands of kilometers under your feet, reaches all the way out into space and physically deflects charged particles blasted at us by the sun. Without it, the same particles that create beautiful auroras would instead strip away our atmosphere entirely, the way scientists believe happened to Mars, which lost its own magnetic field billions of years ago, and lost most of its atmosphere along with it. So here's the full picture now, brought together. Every magnet, from the flimsy one on your fridge to the planet you're standing on right now, is made of the exact same underlying trick, moving or spinning electric charge, aligned in the same direction, generating a field that is not actually separate from electricity at all, but the same phenomenon reshaped by the rules of relativity depending on your point of view. Nobody has ever found a single isolated pole, because you cannot cut a spinning loop in half. Heat destroys magnetism by scrambling that alignment, and Earth itself is only habitable because liquid metal deep underground keeps generating one continuously. The magnet on your fridge and the shield protecting all life on this planet are running on the exact same physics. If this blew your mind even a little, that's exactly why I make these videos, because physics stops being boring the moment you actually understand what's really happening underneath the surface. Hit subscribe if you want more of this. Drop a comment telling me which part surprised you the most, and I'll see you in the next one.